see that Rama could actually give the talk. He's got the script. I never used a script because I found the talk less interesting that way. But today, as I approached NASA Ames, there's a big billboard, and my face is on the billboard. And my dad told me the end of my scientific career would be when my face was on a billboard, because either I was a politician or a crook, or we know you could be both. So, with that background, this is for sure my last seminar. My dad was right. And it's a pretty good span of years, and I did have more ideas than I had time. So that's why I tried to shovel as much as I could into other people's lap, with the possibility that I could cite them, and then they would acknowledge me in the footnote. And they did. So we're going to look at this challenge. There is a plot here. This challenge of how tree physiologists would look at NASA as the only opportunity to scale principles that would make any difference in the world to politicians and to managers. Because what we know locally doesn't scale. And we need to be able to figure out some principles and some way of putting fields together so we can make an impact that makes a difference with our science. And I'm going to give you a sort of a historical perspective, not only of that trend of how we go from principles scaling up, but also the timeline of where we started out with only 6 journals worth reading. It's easy to keep up on the literature. Science, Nature, Tree Physiology, even Tree Physiology didn't exist at that time. So 1% of the literature was worth reading. We certainly read it. And there's a little bit of luck in everybody's life where you have to be ready to take an opportunity when it comes, but a lot of it is luck. And most scientists believe that, but I'm going to document it. So when it started out, my brother, my twin brother, and my sister, who died last week, were born in the middle of the Depression. When Hitler was in power, and my mother's side of the family is Jewish. It wasn't that hard for us. Everybody was poor. Everybody had gardens. And we didn't get polio, because polio vaccine had not been invented yet, and a lot of other vaccines. So we were really, really lucky with our start, even though my father had one job, $100 a month, to support us and my grandparents. Now, during the Depression, very few children were born. And that makes sense, but it gave us opportunities for the rest of our lives because there were very few people applying for jobs, and jobs were available to every graduate, high school or college. I married Doris Carlson in 1957, and she's still with me. Sometimes against her will, but that really makes a difference. And there's a picture of us where we're both smiling. We grew up between the Korean War and the Vietnam War. So even though I was called up for the draft, they said, this guy has flat feet, get rid of him. And I celebrated by walking 9 miles home. Started a career, 10-year track, 12 months guaranteed salary, $12,000 a year. We bought the house for $21,000. I'm just giving you, this is luck. I mean, this is not planned. And I started out when 1/3 of the National Science Foundation grants were funded. 1/3. That's pretty unusual. And golden time funding. And at Oregon State University, I got tenure within about 6 years. And then we had opportunities to take sabbaticals. We took every sabbatical and every leave without pay we could get. We were away for 8 years, each time changing fields, learning about stable isotopes, learning about remote sensing, learning who knows what. So that's pretty special. And of course it's important we both remained healthy so we could travel and do these things. And then when I retired, that's when NASA was starting biodiversity and ecological modeling and climate change. And so here's an opportunity. You don't have to sit on any committees. You write grants, other people do the work, and you continue until last year, the last time. Pretty special, pretty lucky. My education was sort of unusual. I had this really empirical background in forestry, where we had remote sensing, but it was stereoscopic vision to look at the heights of trees and the density. And lots of things, every forest was different, everyone was managed with an expert, and you couldn't generalize. But we knew how to experiment, how to thin, how to fertilize, how to do all kinds of things experimentally. And we had a uniform. At that time, we started out without hard hats, but once we put the hard hat on and the cruiser's vest, we could get behind any lock gate in any national forest in the state. No botanist could do this, okay? No normal ecologist could do this, but anybody, a registered forester, we could do it. Even with logging going on, they guide us through and let us go. So this allowed us big opportunities. Then I went to Berkeley. Berkeley said, you can't do anything until you tell us what's the philosophy behind it and what do you expect, and then we'll let you go out and sample to get the statistics on it. But no measurement before it's time, okay? None. We want to know what you think before you do it. Oh, and by the way, you got 2 degrees, 2 exams to take, one in German, one in French. Then we'll let you start your coursework. Well, one other thing, when you did actually have passed 2 German exams in 2 different universities, you actually had a vocabulary. And you had never mispronounced a single German word because you had never pronounced a single German word. You had only translated them. So when I went to Germany in 3 months in Austria, I actually had the vocabulary, sat in on lectures on the same courses that I was teaching, and say, oh, that's how you say it. Ausgezeichnet, unglaublich. Unbelievable and exceptional. And one of my colleagues, after I wrote this complete article in my very best German, and he was there laughing and laughing, he said, all right, we will rewrite this and you will read it. And of course, in German, that's what you do. So here's the only paper I ever published in German. A few of you might recognize it, but I'm not going to translate it for you today. But these experiences, forestry, very empirical, theoretical, and then application and theory in Europe with visits to 14 countries because we were carrying a pressure chamber that they had never seen and had seen a publication in Science that we published, and they wanted it. So we had the opportunity to meet many, many people at a very important time in my career. Okay, now here's the family. It's not even the whole family, but it's all I can squeeze on here without that. This guy, he was not my PhD student. I hired him at 18, and I figured I made the biggest mistake of my life.
In some ways you did.
Yeah, well, in some ways I did. And Yeah, he's in the upper 1%. He's a AGU fellow, as are 3 other people. And then there's a dean thrown in, Pam Matson there, and a couple others, associate dean, Barbara God. So this is just part of the family, but you know, how did we ever get these kind of people to come to Oregon State when I was in my 30s and 40s? So very, very fortunate, and we stay in touch. By the way, there is a NASA person there called Hank Margolis that is still quite active. Okay, well then, there's other people I wish I could have recruited, but you meet them when they're graduate students or the first year of their postdoc, and they go on to do magnificent things, and all you do is pass on their name and say, I wish I could have this student. And Indy Burke's a dean at Yale. I knew her as an undergraduate. And it's like, they're friends for life, because when you turn about 30 or 5 or 40, and you discover somebody like this and get enthusiastic about them, they seem to remember that. And so you set a network that you had really nothing more than recognizing talent. And that's really important, because I think in the long run, it advances science so much faster than it would otherwise. Okay, now I have to fess up. There are 3 other physiological ecologists who have been lifelong friends. This is a very special picture. This was taken in South Africa the day that Paul Jarvis was into the Royal Academy of Science. He died about 3 years ago. So Suni Linder is the best experimentalist that I know, both in Australia and Sweden, and invites everyone in to share the setup that he has. Joel Landsberg is meteorologist, co-author with most of my publications in the last 10 or 15 years. And I think all I did was take their ideas, talk day and night to them, of course, drive them nuts, and introduce them to my students and other people. And these people, these are world-class scientists. Not the guy on the left, but the other 3. And the way we were able to move money and opportunities around was we always kept our word. Such a simple thing to say. We could have overcommitted, we were overcommitted, but we always kept our word that the money would be there, we would come there, these people would do this, the publications would come out. It was hard to do, it's hard on the family, but we did it, and I think it's the one of the messages that I'll have, I think, to apply to all of you. Okay, now come the stories. When we first got to Austria, a mountain man, Walter Moser, arranged for me to fly into a glacier where they had a setup where they had meteorology, and the winds were so strong that when it went above 100 miles an hour, the towers folded themselves down automatically and then only came back up when the wind was less. Very clever. And they had a wonderful Italian dinner prepared for me as we landed. And I ate it. And then I got in the plane. And then I barfed over the whole side of the plane, and it froze. And I didn't get any more invitations from this glider pilot to ever go up in the air with him. And he even told me that he used to fly Hitler. And I said, well, isn't that ausgezeichnet? Anyway, stories are memorable. If you tell your science as a story, your students will repeat them. They keep introducing new things that you didn't say. You know, you're in denial, but it's still a good story. So there are some people that introduced me into remote sensing beyond stereoscopic vision. And it was interesting. Alex Getz was at JPL, and I got this call to come, and I said, well, you know, every physiological textbook shows the absorption spectrum for photosynthesis. You don't need me. I mean, here's a page, I'll send it down to you. And he says, no, you don't understand. He's German. We need you to understand what the restrictions are on data load and imaging spectrometry. Had a lot of restrictions in those days. It still does, but less. And so I went to these meetings and I learned a lot. Signal to noise ratios and the atmosphere that's in between the leaf and that. And I met Sam Goward at Maryland, and he asked me, what's going on in the West here where this sort of bare spot? And I said, oh, that's serpentine. And he said, well, what's down here? And I said, oh, that's limestone. He said, we need you. You've actually been in every state in the West. You know things that we can only speculate about. And I said, okay, I'm speculating about remote sensing. So this is really important work, and we started on the ground with a spectroradiometer, getting the spectral signatures of end members. Okay, there are some slight differences between the way physiologists used to approach their science and remote sensors. I'm going to simplify this. Physiologists look for general principles. So what control water flow through plants from the roots to the stem? They look for what controls photosynthesis and the biochemical cycles. They look at what each mineral that's essential for growth does, regardless of the plant. As long as it's a green plant, that's what physiologists are looking at. Like Berkeley, they'll say, okay, if this is true, if water is now in a frozen state, what will happen? They'll say the stomata will close. They'll say, well, if you're in the tropics, you just killed the tree. Okay, those are general principles. So that means that every model we ever have has to have, is the water frozen? There's all kinds of hydrologic models in the tropics that don't have, is the water frozen? But if you're going to have a general model, that has to be an if statement in your model. And you predict response over time. What's going to happen if you change the temperature, change the soil water, change, what do we expect? So now we can go out and test, are the trees dying where we said there's a drought? Are the trees dying because there's air pollution? Those are hypotheses where it's used remote sensing to test the predictions rather than to document it. There's a difference. So originally, the remote sensing I was introduced to was supervised and unsupervised classifications. Right back there in forestry, impossible to scale, because each little system uses different end members and different combinations. So we were looking, where Alex Getz was looking for geology, for principles that would scale. So we're looking in the laboratory with gear borrowed from Sam Goward at fertilized and unfertilized canopies, where we wanted to know what's the wavelengths in NDVI that really make a difference and really measure absorbed radiation or photosynthetic capacity or chlorophyll. Well, certainly didn't measure chlorophyll. So here's a paper looking at what does this signal that everybody used in remote, what does it really measure and what doesn't it measure? And so Barbara Bond there is, that was her very name. She did this with data and information provided by Sam Goward. Okay, then we take baby steps. We're still in forestry. We're still using stereo and video cameras with blue, green, red things. And our instrument, our platform is not going to go more than 500 feet above the ground with spectroradiometers and calibration panels on this. And unfortunately, no GPS. We had no idea other than we'd stand out there and that, here, plane. And we got a paper out with Warren Cohn where he was looking at it with a satellite over the same area, and we were on the ground measuring how much light comes through, what the leaf areas, and which trees are or are not dying. And behind that, there's a series of 4 publications knowing what happens when you fertilize these trees, what happens when they're under water stress. So we had the physiological background understood pretty well. Well, then we went to Harvard, and they had a tower and 10 years of data, and we had the ultralight flowing over 4 seasons. I picked the colorful season. The one without leaves is not too impressive. The one with green leaves is not too impressive, but the autumn color really is impressive. And then there's a little tower, which I'm not allowed to point at with a laser because I will destroy the screen. And these towers allow you to climb and measure various things, including the photosynthetic capacity directly. And so you can make inferences and get a paper out and sort of move up in scale. But the people that really moved up in scale is Raman Amati and Steve Running, no longer 18, by the way. This is at his retirement party, which we're not sure is going to stick either. And Bev Law pointed out that just 6 more inches to the right, there's a little sign that says, "This way to the toilet." And I'm not allowed to put that on this slide because I don't want to embarrass Rama. But in ecology, this was the first color image ever published. And guess who the technical editor was? So they had to change their philosophy. They had to open it up to remote sensing, and they had to have color imagery. But then we really became indebted to Dr. Mike Ryan, which on almost every respiration paper in the world, his name is mentioned somewhere. And Michael Ryan's thesis was separating the respiration from stems from the growth of the stems. In both cases, you get respiration. But if you get a certain amount of water stress, there are no cell divisions. At certain times of the year, for the day length, there are no cell divisions. So you could tease out the relationship between temperature and respiration for maintenance versus growth. Growth cost is the same whether the cell is laid down at 2 degrees Celsius or at 30 degrees Celsius, same cost, 25% tax. And then there's correlations that Bev Law here is helping establish where she's measuring CO2 efflux from the soil. And we thought, well, that's just decomposition going on down there. And then we found out that on poor soils, a lot of the carbon ends up as sugars and amino acids being fed to the free-living fungi. And if you girdle the tree or put a cold block around it, within 24 hours, the CO2 efflux from the soil is cut by 50%. So suddenly we're saying, wow, we thought it was just growth of fine roots and stem and like that, but it's like these products are sugars and spices and everything else that's nice. And if you measure litter fall, sometimes you can get a correlation between the carbon in the litter and the CO2 coming from the soil, and you can make certain assumptions. I think you see the advantage of putting a question mark in this title, gets you by half the reviewers pretty quickly because they're all I don't know. I don't like this very much, but he's got 12 points rather than his normal 3. It's important and it's testable. So by God, we'll let it by. And so there's my favorite kind of line, R².98. From New Zealand to across the Oregon Transect, fairly good sample. Mike will tell you that in the boreal forest, they don't recover fast when there's lots of light in the springs. So the ratio is not roughly 50%, it's more like 30%. He had his hand up, otherwise he was going to make an injection. No, I wouldn't do that. Okay, well then my favorite NASA project came out of this NASA Ames. And Dave Peterson was in charge of all the airplanes. And there were lots of platforms, 9 platforms, including Canadians and our lightweight, flying over Oregon at 6 different points. Total range of primary production in North America forests, 10-fold difference. I like subtle changes that you can test ideas rather than you're all close to the same point. And AVHR, you can see some differences in the NDVI or greenness index. This is really the high point of my career of working with colleagues in NASA. And 6 of those are my graduate students. Sam Goward's there, Jane Peterson's there, I'm there with hair, more hair. Pam Manson's in the front row on the left. Well, this is my classic photo, Friends of Dick. Still, I just want to list some of the names so you can see we had the ground troops and the airborne. And we told each other stories in order to educate what we were measuring, what we were interpreting, what problems we had, and who had to go out and make more measurements. We had priorities that Pam Matson helped us set. Very, very important opportunity, very good colleagues, wonderful collaboration. So finally we reached the point where we want to take the physiological principles and some remote sensing, and we want to scale to predict on-the-ground growth of ground trees. So we have to know 2 things about the soils. We have to know whether it's fertile or infertile, and whether or not it's drought prone, because it has low water storage. You have to run a hydrologic model. And then if it's fertile, less than 25% of all the carbon is going to go below ground. If it's infertile, really, really infertile, up to 70% goes below ground. So we're shifting the allocation, and then we have more than 3,000 field plots, which we can batch in certain things, certain packages, and our R² is only 0.98, so we're failing again, but we're getting close to knowledge. What we didn't know is the age of the forest. We needed LiDAR, and we didn't know it, and without the age of the forest, you get an average value, but you don't get the real value. 2 very important people. Nicholas Coops, I took to lunch when Steve Running didn't have time for him. We ended up publishing 25 papers together, 17 on climate change since 2010. Sometime if you want to ship money across the border, you'll have to come talk to me. Thomas Hilker, brilliant German that came to Oregon State University, died at age 40, heart attack. Oh my goodness. So, had some sadness, but had some pleasures too. Okay, this is my favorite experiment when I was growing up. I had 3 years of opportunity with Gary Pittman, Dr. Gary Pittman, who came from Boyce Thompson, having the pheromone that attracts bark beetle in his hand. One other thing, he's 6'2". He's 230 pounds. He used to be a lineman for Berkeley. Why is that important? We cut down 400 trees. I cut down 50. He cut down the rest. All right, I mean, this is a true story. And we did various things. We fertilized, we thinned, we added sawdust to tie up nitrogen. And then, my wife is still holding her head, but we got a cheap deal on a ton of brown sugar. Well, brown sugar doesn't spread, it turns to bricks. We said, okay, we'll fix that. We'll dry it out, put it in a kiln. We put it in a kiln and turned it into stone. So we're out there with a little sieve, spreading a ton of sugar to tie up all the things. Because our interest, unlike foresters, we wanted to perpetuate an outbreak by tying up all the nitrogen that would normally be released as the dead trees would shed leaves and the recycling would take place. And in 3 years, the end of the end of the NSF proposal, we had the publication, we had reversed the system, or we had maintained it. So it was really nice. But what we didn't understand at this time, we had another publication, went across all of Oregon, on lodgepole pine, 140 years old. And we kept reading in the papers that in Colorado, you should have this many trees per acre, or this much leaf area. And in in Arizona, you should have less, and in Oregon, you should have less. It was always different. And so we finally found out with a remote sensing paper that it was related to the maximum leaf area. If you thinned about 2/3 of the forest and left the trees evenly spaced, they became immune to bark beetle attack. But it was irrelevant what the number of trees were. It was the leaf area index. And so you could see we had a bigger index, how much growth per unit of stem per meter squared of leaf. So if it's a great big tree, has lots of leaves, it has to put on an awful lot of growth to be safe from beetles. If it's a little bitty tree and it's got lots of light and it's got adequate water, it doesn't have to put on much growth because it's per unit of leaf area. And here we are rediscovering from our own data 20 years ago, some principles at scale. Makes you pretty happy. Well, Jean, there she is. She's smiling just before she pulls the trigger on this cannon. This is a 12 gauge magnum load, full choke shotgun. It kicks small people down steps. And there I am with this instrument, about ready to put a twig in and look at the foliage and see how much pressure it takes to bring water back to a cut surface. And Steve Running almost never made it to age 19, because when I went on sabbatical, he was taking this one-of-a-kind instrument into the field, and he has a fast turn screw on top. And he was out there, and he screwed on the top, and it bounced down, bounced up, went down an 80% slope, and got caught in the branches of a madrone tree. It saved Steve. And so from these kinds of papers, background papers done 75, 97, 2001, we have a background paper here where we're doing water budgets and predicting where mega fires are going to occur with a 70, 80% accuracy without knowing whether there's lightning, whether they're thinned or unthinned. So when the forest really dries out, because it runs out of water in the soil, some of these principles do indeed scale. There's the model from 1975. I think it's the first simulation model of tree physiology tested in the forest. Okay, so this is for me, my last lesson. The only thing I've gotten better at since I officially retired is trout fishing with a fly rod. I'm 100%, 200% better. And then the other thing that's happened is I have these nearly normal relatives, my family, and they produce this extraordinary grandchild. So we're spending a little more time than I ever thought we would, since my son was 52 or something when he got married to his wife, and so this is something. But this is what I want you to take home, because this might actually affect the way you do science, or have been doing science, or could be doing science. You're going to be very busy. You're going to have lots of opportunities. Some of them are worth taking, some are just at the time when you're ready. Take them. Take them. You'll learn some new things, you'll grow, you'll meet new people. And then recognize talents in others. No one's going to be put off if you go up to the poster and you say, this is really good, as long as you don't do it for every poster in a row. Be a little bit selective. And you'll make better and better judge as you go along and see what these people do. But it's really, really worthwhile. Tell science as a story. Before you write your paper, write a 100-word abstract. Okay, write 300. I'll edit it to 100. Science requires 100 words, all right? Once you've done that, that's your story. That tells you why it's important, what you're going to do about it, and what difference it makes to anybody else. If you can't write those 200 or 300 words, you're not ready to write the paper. Oh, you can write the methods section. That's really important. It took a while for me to learn that. I've never gotten over it, obviously. Keep your word. That's how you really build trust, because you don't own these people. You don't fund them. You said you're going to do something. Do it. And hope your health holds up. And make the process fun. Good grief. You can't keep going 50 years unless you're enjoying it. And other people should enjoy it too, except that you keep talking all the time, every time you meet them. Well, thank you very much for this honor. It's very, very special.